This is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to learn about binary tree traversal techniques. Before going to traversal techniques, first of all, let's understand what nonlinear data structure is. Then, what do you mean by nonlinear data structure? A data structure is one in which data is stored in a fashion. It can be in continuous memory locations or in random memory locations where one piece of data is linked to another piece of data using addresses, by storing their addresses. And the structure of the data will be in the form of a node. Let me show you how it works. Then, nonlinear data items are arranged in non-sequential order, and they are arranged in a way to process the data in such a way that one data is not even related to a single element but to many elements. So graphs and trees are the basic examples of nonlinear data structure. Let me show you a small example of the same. This is a structure of a tree I'm drawing right now. And here you can see that the first node, which do not have any parent, is known as a root node, and the children which come out of the root node, which are connected to the root node, are its children, and who are in terms of the root, the nodes which are connected in the second level are its grandchildren. Okay, so you can see a kind of hierarchy over here, where the root, even in few textbooks, it is also mentioned as parent node, right? So this is the structure of a tree, where cycles are not seen, right? And it is a one which extends itself in downward direction, right? The another kind of nonlinear data structure is a graph. And here the circles represent the nodes or vertices. You can see that the cardinality of each and every element is needs not only one, it can be more than one. Every node can be connected to all the remaining nodes also. So this is a graph. Here, in terms of trees, you can say that every operation starts from the root, whereas in graphs, we don't have any such node which is at pinnacle, which represents itself to be the starting node of a graph. So each and every node will be enjoying the same priority, right? So these two are two kinds of non-linear data structures which we have in the concept of layers, right? So coming to the advantages of having or holding the data in terms of non-linear data structures. Here the case is where in a file system, say a file system. Example, in your system, have a look at your C drive or D drive. Say C drive. Within C drive, you might be having a folder saying movies, right? In that folder, you might be having many movies, say randomly, say some ABCD movie, right? Within that, you might be having songs, right? Songs. So in that songs or movie, coming to songs, you might be having some ABCD dot MP4, right? So one after that. In movies, do you have in the theater? Do you have only one folder on the name of movies? You can have programs within which you have categories like Python, Java, many, right? So that itself shows you a structure of a tree, right? Coming to the basic example of a graph, networks. My dears, I hope just recollect the concept of networks, where a source node is connected to the destination node by using intermediate nodes, right? If you send a mail to your friend, someone in US, then that mail is going to touch intermediate servers, hubs, and routers to reach your friend, right? Virtually. So that network itself is a basic example of graphs. Google Maps is an example of your graphs, live examples of your graphs. So cases where the relation of a data is not to a single another data but many, then we go for non-linear data structures to store them, right? So have a look at binary trees. Let's specifically know about binary trees, a category of a tree in which there is a restriction that every node, including the root, all the interior nodes. Okay, so what are interior and what are external nodes? So the leaf nodes, say 2, 5, 11, or 4 are known as leaf nodes because they do not have any children, right? Or 2, 7, 6, 9, 5 are known as internal nodes, interior ones. Interior, exterior, internal, external. We can use these kinds of words to understand them. So internal nodes have a constraint saying that they can have maximum of only 2 children, minimum 1 and maximum of 2. And leaf nodes, they have 0 children, right? Have a look at the root node. It is having 2 children. Coming to the node on its left subtree, it is 7, right? It is having 2 children. Coming to its right subtree, 5, it is having a single child, right child, which is 9, right? Got it? So if in a tree, if we put a constraint saying that every internal node can have a max of 2 children, then such a tree is known as binary tree, right? So now let's look into how to travel, how to touch each and every node in a binary tree. That is the main point we are supposed to discuss right now, right? So these binary tree traversal techniques are in 3 different categories. Have a look at this tree. Coming to linear data structures, whether it is stored in contiguous or non-contiguous memory locations, as every database is connected to a single another database, it will be quite convenient to locate them. But here, you start from the root. That starting point you might understand, but how to travel, whether to choose the left-hand side or the right-hand side, that is a big dilemma, right? So there are different traversal techniques that have been developed to perform binary tree traversal, right? So let's have a look into that. So the first and foremost one is in-order traversal. In-order traversal, all the traversal techniques, in-order, pre-order, and post-order. These are the 3 traversal techniques, and all the 3 traversal techniques are recursive in nature. Starting from the root node, they are going to execute the same funda or the same pseudocode for all the nodes unless they reach the leaf node. Because binary trees tells us that every node can have internal node can have a minimum of 1 and a max of 2 children, right? So let's have a look into the in-order traversal first of all, right? So in-order traversal, it works on the basic in-order funda. Have a look at this one. See, it first of all runs towards left-hand side. When it reaches the end, it prints the root. Then it travels to the right? So using recursion, the function will call itself on the left subtree. Then it prints the current value. Then it calls itself in the right subtree, right? So the basic usage of in-order traversal is to get the in order of data, that is ascending order of data in case of binary search trees. The conditions apply, my dear. So binary in storing data in binary tree, it does not impose any rule saying that the left hand side data should be smaller, the right hand side data should be higher. No such kind of rules are imposed on binary trees. So if you convert your binary tree into a binary search tree where such type of rules are imposed, then when you draw an in-order traversal of a BST, that is your binary search tree, data will be retrieved in terms of ascending order. It is a good point, guys. Please make a note of that. Let's see an example of the same. This is a binary tree. You can see 8 is the root of the same, and its left subtree is headed by 4, whereas its right subtree is headed by 10, right? So let's perform in-order traversal of the same. So have a look at the funda I have taken. So in-order is left, as the pseudocode tells us. First prune towards left, print the current, which is the root, and then travel towards the right subtree. So to print the same, to make a note of our traversal, right? So I have taken an array, blank array, okay, which is not filled with any data right now, and the size of this array is equal to the number of nodes. Please make a note of this one. Size of array is equal to number of nodes, right? So as when number of nodes you have, declare then array of the same size, right? So starting from the root node, right? So what in-order tells to travel in the leftward direction. So from the root, take the path towards the left. So as you have taken the path towards left, you are going to encounter 4. Once you encounter 4, you have to travel towards left because 4 is still having a left child. When you reach 2, do you have a left child for 2? No. As you do not have a left child for 2, the left traversing towards left comes to an end. What is the next step in our algorithm, recursive algorithm? Printing the root. What is the value of the root? 2. So print the same or copy the same into your array. Then what is the node which is right to your 4? See, coming to the root as we have printed 4. Now you have to travel towards the right of 4. Have a look. So coming to the right side of 4, 6 is present. Do you have any left child of 6? No. Then print the root. What it is saying? If left is not present, print the root. So you have printed 6. Do you have any right child for 6? No. As you do not have any right child for 6, travel in the upward direction, because the traveling towards the left of 4 is done. Printing of the root is done. Right side traveling towards the right of 4 is done. Right? As a whole, working with the left subtree of 8 is done. Right? Once that is done, what you have to do? You have to print the root as the left subtree job is done. So store 8 in your array. Store 8 in the array. Now let's start the same process, recursive process with the right subtree of 8. So let's travel towards right subtree of 8. Right subtree of 8 is headed by 10. Is it having any left subtree? Yes, it is having. So move in that direction. Okay, so once I move in this direction, do you have any left child for 9? No. So if left is not there, what you have to do? You have to print the root. So what is the value of the root? Which is 9. So print it. Do you have any right child of 9? No. As you do not have any right child of 9, travel in the reverse direction. Go to the root. Why? Because tuning off, traveling towards the left subtree of 10 is done. Once working with the left subtree is done, you have to print the root, which is 10. So in the index value 5, the value 10 is stored. Now, as the left subtree of 10 is done and the root itself is printed, let's travel towards the right side of 10. Right side of 10 is headed by 11. Is it having any left child? No. As it is not having any left child, print the value of the root. What is the value of the root? 11. So print it, that is store it. Right? I have stored it in index value 6. Right? Then, is it having any right child? No, as 11 is not having any right child. So have a look at this one. 11 is the last or the right to most leaf node. Traveling in that direction has come to an end. So with that, we can say that we have come to the end of Inorder traversal. So as the the right subtree of 8, which is headed by 10, is traveled in both the directions, right? So even you can see that the array which we have taken, which is equal to the size of the number of nodes of your tree, is full. That itself tells you that okay, we have touched each and every node of this tree. As you can see that this tree is a binary search tree because have a look at this one. All the elements in the left subtree of 8 are less than 8, whereas all the nodes in the right subtree of 8 are greater than 8. The same funda is repeated for its children also. So the final list which you get after performing Inorder traversal is in ascending order or increasing order of their values. Okay, I hope you understood Inorder traversal by now. Let's go with the next traversal technique, which is Preorder traversal. Right? So even Preorder traversal is a recursive function where we are going to print the current node first, then travel towards the left subtree. Once left subtree is done, travel towards the right subtree. So in short, we can say root left right is the short form for preorder. The basic usage of a preorder is you will going to find when you go for prefix expression of a given expression tree. Expression tree. What do you mean by that, ma'am? So, for example, you have an expression a plus b. It can be represented in the form of an expression in this way, expression tree, where plus the operation represents the internal node, whereas the operands are going to stay at the leaf nodes. Or shall I extend this expression for you guys? Let me extend this one. Multiplied by c. As multiplication is having a higher priority, b and c, whatever the result you are going to get will be added to a. So can you see that? Can you observe that? All the operands are the leaf nodes and the operators are the internal nodes. So have to write a prefix of the same. So prefix of this tree will be plus, right? So first the root, then the left operand followed by the right operand. When you come to the right subtree, again goes with the same funda. First root, then left, then right. This will be the prefix expression of the given expression, which is used by the internal arithmetic logic unit to evaluate expressions, right? To evaluate few expressions, prefix expression is used. That will be the basic usage of prefix expression. Let me explain you the same with a small example. Let's have a look at this one. The same tree which I have taken earlier, I'm going to take the same preorder. Okay, so the funda of preorder I have mentioned over here, right? So let's always remember, guys, it can be a tree, binary search tree, or any kind of tree. At the beginning, we just hold the address of only the root node. So even you perform insertion, deletion, or search operation, you have to start from the root node. So let me start with the root node, which is 8. So coming to preorder. Preorder, what it is saying, so print the current one, which is 8. Once you print the current one, travel towards left. So once you travel towards left, you are going to encounter the left subtree of 8, which is headed by 4. So as it is headed by 4, the heading, you have to store it. So 4 is stored at index 1. Again, travel towards left. When you travel towards left, you are going to encounter 2. So first of all, print the current one. Store the current one, which is 2. Now, once you are done with it, you have to travel towards its left. Is 2 having any left node? No. If left is empty, go towards right. Is it having any right node? No. Then what? Go in the reverse order, because 2 is a leaf node. It doesn't have any children, either left nor right. Right? So let's go in the reverse direction. So traveling towards the left hand direction of 4, node 4 is done. So let's go towards the right side of 4. When you go to the right side of 4, you are going to encounter the value 6. Right? So when you encounter the value 6, so first of all, the preorder tells store that value. I have stored 6, and then I'm going to travel towards its left. Is 6 having any left item? No. Then travel towards its right. Is 6 having any element on its right side? No, as 6 is a leaf node. So job is done. So traversing towards the left and right of 6 is done. So let's go back. Now you can see that we have covered traveling or covering all the elements that are present in the left subtree of the given tree. So as it is a preorder, root is done, left head is done. We are left with right subtree. And this right subtree is headed by 10. Preorder Traversal tells us that first of all, print the current node. What is the value of the current node? 10. Print it. So I have stored the value of 10 in the index value 4. Once it is done, you have to travel towards the left hand side of 10. Once you travel towards the left hand side of 10, you are going to encounter 9. Preorder tells us to store the current one. So I have stored 9. Then again I have to travel towards the left hand direction. Do I have any element in the left? No. Then I'll try to search for an element in the right hand side of 9. Do I have any element in the right hand side of 9? No. As 9 is that is a leaf node, it does not have any left or right children. Right? So it is going to go in the reverse order. When it reverse preorder, root is already done. 10 is already been counted or entered. Right? So let's go towards the right side of 10. Once you reach the right side of 10, it is headed by 11. As it is preorder, first of all, print it or store it. I've stored it. Right? So do you have any left child of 11 to travel further? No. Do you have any right child of 11 to travel further? No. Both are not there. So the right subtree of 8 traveling with the right subtree of 8 is also done. And even you can check that the number of nodes or the array which we have initialized with the size of the number of nodes in the tree is full. That itself tells you that preorder traversal job is done. Have a look at this one. Preorder does not give you any guarantee saying that the final resultant or the traversal order will be in some form. It will not promise you on anything, right? You can see the orders 8, 4, 2, 6, 10. It is neither ascending nor descending. Okay, let's have a look at the next or the last post order traversal technique. Contrary to the pre. In pre-order traversal, we were thinking of the root first and then the left subtree followed by the right subtree. But in post-traversal technique, we are going to push the root to the last. Mane, first traversal in the left direction, then right direction, then print the current node, right? So here the root node, say the current node is given the last priority. So then what is the usage of post order? Post order or usage will be in expression evaluations. Post order traversal. When we convert, generally humans understand in fixed expression. Am I right? If I say A plus B, you will understand. What if I say AB plus, will you be able to understand this one? No, right? So humans understand infix expression, but system understand postfix expression for expression evaluation, right? The total logic of how to evaluate a given expression is been already demonstrated in my previous videos. Please go through that once if you need, right? So coming to post order traversal, they'll be used for conversion of infix to postfix, as well as they are going to use stacks as an intermediate medium to evaluate a given expression. Okay, please refer to my previous videos to understand the usage of post-order traversal in depth. Let me give you a demo of post-order traversal using the same tree which we were considering for in-order as well as pre-order traversal. Let's have a look at this one. What post-order tells? First of all, travel towards the left, right? So that's what I'm trying to do. I encountered 8. Is 8 having any left node? Yes. Travel. So, right? So I have touched 2. Is 2 having any left? No. So I cannot, coming to the funder, as it is, I cannot travel towards left. I'm going to try and travel towards right. Once I travel towards right, is 2 having any right child? No. As 2 is not having any left or right child which is not being traversed, I'm going to print the root. So 2 is being stored as the first element of my post-order traversal. Once it is done, you have to go in the reverse one. So I'm going to travel to 4. So 4 is the root node. Its priority is at the last. So once left subtree traversal is over, we need to travel towards the right subtree. Once we travel towards the right subtree, have a look at the node 6. Right? Is it having any left child? No. Is it having any right child? No. So what post order tells? If left and right are not present, then print the root. I printed the root or stored the root. So traveling towards the left subtree as well as right subtree of 4 is done. So what it is saying, if left is done, right is done, go with the root. So print the root, right? So left of 8 is done. As a whole, traversal towards the left of 8 is done. So now let's travel towards the right of it. When we travel towards the right of it, you can see that it is headed by 10. Is 10 having any left child? Yes. 9. 9 is the left child of 10. As 9 is the left child of 10, is it having any left child further? No. Is it having any right child in the further? No. So as left and right, both the cases are not there, go with the root. what is the value present in the root? 9. Kindly store it. Now, traversing towards the left of 10 is done. Now, let's move towards the right of 10. Once you travel towards right of 10, which is headed by 11, check whether 11 is having any left child or right child. As it is not having any left or right child, store the current one, which is 11. Right? So I have stored 11. Once you have stored 11, go back. So in view of the node 10, traveling in the left side direction and right side direction is done. So now root can be stored. So I have stored the root value 10 in the given array. Now in view of 8, even the traveling towards the right subtree is also done. Once it is done, we are left with the root node. So what is the root node? 8. Just use it and store. So this is the order in which you are going to get the values. You are going to get the values if you are going to travel using post-order traversal technique. Yes, I hope you understood the 3 traversal techniques that we have in terms of binary trees. One is in-order traversal, pre-order traversal, and post-order traversal. Right? So, at times, we might get questions saying that, see, previously they have given a tree and they have asked you what is the pre-order, in-order, and post-order traversal of the given binary tree. The case may not be the same always. You may get queries in your competitive exam saying, what if pre-order and in-order means one traveling technique is given and you are asked to construct a binary tree out of it. Yes, this is a very important question in GATE point of view. Right? Those who want to pursue PG. So this is one of the major questions we regularly encounter in case of GATE exams. Okay, so let's have a look at the question which I have given. Pre-order and in-order traversals are given. So I have to construct a binary tree out of it. Have a look at this one. I have used 3 different colors, my dears. Red color for root or the root of a subtree or main tree, whatever. Red is for that. And blue color I have used it to represent the left nodes and green for right. Please understand that. Okay. So for your convenience, I have colored. Okay. Guys. So have a look at this one. In pre-order, what we understand with pre-order? We understand that initially we are going to consider the root node first. Am I right? So in the given series, whatever node that is used as the first one, which is G, will be the actual root node of the binary tree. Okay, so search for that node in your in-order. Search for G in your in-order. So what are all the elements that are present to the left of in-order will be present in its left subtree, and all the elements which are in the right side of G will be on the right subtree of the final binary tree. Okay, please remember this one. Pre-order traversal. Pre will be used to identify root, whereas infix will be used to identify left and right subtrees. Left and right subtrees. Okay, guys. So please keep this in mind. Pre-order traversal is used only to identify the root, whereas in-order is used to identify the left and the right subtree values. Okay, so here we have taken the first step where we have identified the root of the tree and its elements which will be present in the future in its left subtree as well as the right subtree. Let's start. So have a look at this one. Let's consider only the part which on the left of tree. Okay. So what is the second element in preorder, which is B? Try to locate where it is in order. Here it is. So B is the element which is going to head the left subtree of G. Okay. So what are all the elements that are present? Left to B will be the left child of B, whereas all the elements which are right to B. Guys, remember G acts as a boundary because we already know that G is the root of the binary tree, final binary tree. So G acts as the boundary. So K, C, F, A will be the part of a right subtree of B. Okay. So let's move further. So we always take a step from one step to other. We need to go through the what is the next element in the preorder because preorder decides what will be the root, right? Let's do that. So in the next one, Q. Next element in your preorder is Q. Where is Q sitting? Q is over here. Are there any elements left in the left side of Q? No, we do not have any elements on the left side of Q. Coming to the right side, even though we have B, B is already been used as the root of left subtree of G. So we cannot reuse it. That itself tells you that Q is a leaf node because it do not have any right child or left child. It is a leaf node. Fine with it. Let's go and consider the next element. The next element in your preorder is A. Locate where A is in order. Here it is, right? So what are the elements which are present in the left of A? Please see, understand that B acts as a boundary because B is already taken, right? So K, C, F are left of A. What are the elements that are present in right of A? Right of A, I don't think any element is present because G is the root which is already been taken. Do you see any element which is not, whose position is not yet been decided? So I hope you can see that K, C, F are the elements whose specific location is not yet been identified, whereas G's location is identified, which is the root of the final binary tree. So only case A is having only a single left subtree, which is K, C, F, which is going to hold these three elements. We don't know what is the order. Let's see in the future how we are going to do that. Okay, let's check for the next element in your preorder, which is C. Right? So C is the next element in your preorder. Locate where it is in your order. Here it is. So what is the element which is present left to it? K. So K acts as the left child. Guys, remember B is the boundary here and your A is boundary here because A is already taken. We know the right position of A, right? What is the right of C now? F. F is the right of C. Have a look at this picture. Can you see the left subtree of A, G is totally filled? Yes. Right? So let's consider again the next element in preorder, which is K. So K, here where is K in order? Here it is. Left of K is B, whose position we already know. Right of K is C, whose position we already know. That means K do not have any left or right child. Means K is a leaf. Okay. What is the next element? In preorder, F. Have a look at this one. After K, you have F in preorder. Its position in order is here. What is the element which is left to it? C. C's right position is already been decided. Right to F is A, whose right position is already been decided. Right? Then let's see, job is done in the left direction of F. Right? Left and right. So this tells you that F is a leaf node. Next, coming to the next element in your pre-order, which is P. Right? So P, coming, where is it in your in order? Here it is. You do not have any element left to in order. G is already been taken, my dear, which is the root. Coming to the right, E, D, H, R. These are the three elements, four elements, sorry, which are going to be placed in the right subtree of P. Let's see what will be the order in future. Next element in pre-order is D. Where is D in order? Here it is. The in order is in order, its left element is E and the right elements are HR. Right? So place them. What is the next element in pre-order? E. So in order, where is E? Here it is. The left child of E is P, which is already taken. A right child of E is D, which is already taken. I cannot use them. So E is not having any left or right child, so it is a leaf node. Next element to be considered in pre-order is R. Where is R located in order? Here it is. What about the left child of R? H. H is not being taken yet. So we can split R and H. So R will be acting as the parent and H will be acting as the left child. Do you have any further elements on the right side of R? No. So R is a node which have a single left element but not any right element. Right? So what is the next element in pre-order? H. Where is it in order? Here it is. So its left child is T, which is already been taken or used, and its right child is R, which is already been taken and used. Right? So it tells you that as H cannot have any left or right children, it clearly tells you that H is a leaf node. Right? So, and in the pre-order, this is the last element which we have taken. So, construction of binary tree for the given pre-order and in-order combination is done. You can see that in the whole tree, each and every element is placed in its right position. There's, if you want to cross-check, kindly write in order and pre-order of the same and check whether it is equal to the list which is given in your question or not. Reverse engineering, guys, simple point. Okay, with this I would like to close. I hope you understood what a binary tree is, what are the traveling techniques in binary tree, and how to construct a binary tree using pre-order and in-order. Okay, thank you, guys.
Like, share and subscribe. Hit the bell icon for more updates.